Let's begin with the presentation by Afra María Pertusa. Afra joined AIMEN at the end of 2020 in the Advanced Robotic and Technology Applications unit. She has a degree in robotics engineering and a master's in industrial IT. She is currently pursuing a PhD focused on dynamic task composition for robotics control architectures. At AIMEN, her work is centered on high-level system and robot control development, integration, and demonstration of developed solutions, as well as the technical coordination of a national project. So let's start. The floor is yours, Afra.
Thank you for the presentation. And now we are going to move into this webinar that is for high-payload robots, the safe human-robot interaction. So this is part of the CONVERGING project, and the contents that we are going to follow is introduction to what the XXL Pilot Factory is, and also the use case here at CONVERGING, and then the speed and separation monitoring and the hand guiding that are both safety measures. Here you can see the pilot factory, that is an open space that we have here at AIMEN. It is an environment that has real components. Right now we have naval components, and also we are integrating an open work cell to work with the operators. That is the picture that you see here. And these spaces and this infrastructure is quite useful for us to test the developments before going to the final user or the industry, because we can replicate the conditions that we will find there. And as we work with sectors that are quite difficult to access, like is the naval industry, because of their production times, we can test it here before going there. So we ensure that the systems will work. And here in the CONVERGING, we are using the open space cell that is focused on the manipulation of heavy additive manufacturing elements. And here we are applying safety components and also the hand guiding system. It's quite different a little bit different to what we are going to present, because the safety elements here are commercial ones, and the hand guiding is a solution that another partner developed, but now we are going to focus in another kind of solutions that we have developed here at AIMEN, that the purpose is the same, to ensure the safety and the safe interaction with the operator. And now here at AIMEN, we have developed a hand guiding system and also some safety systems that we are going to cover. But first, as we are talking about safety, we have to take into account the certifications that are associated to that. The first one is the ISO TS 15066. That is the one for robots and robotic devices and the collaborative robots, and the safety interaction between the human and the robot in a shared space. So this normative define 4 modes of working that you can see here in the picture. We have the level 1, that is the safety rated monitor stop. That the thing here is that when the operator enters the area, the system will stop. The second mode is the hand guiding, that here the operator can directly contact the robot and move towards the direction the operator wants. The third level is the speed and separation monitoring. Here we monitor the distance between the operator and the robot. We can use different techniques to do that, and we will work in normal mode, reduced mode, or we will stop the robot. And the last mode that they define is the power and force limiting. That this is, if you have used the robots, it's the typical from the UR. If you apply more effort, the robot will stop because it has some sensor in all the joints. So when some overload is applied to one link, the robot will stop. And this is all for the first certification. And in the second one, we have the EN1005X. that this is more on the human physical performance. And the aim here is to avoid the operator to use the heavy loads, and it's also focused on ergonomics. So with the solutions that we are going to present, mainly on the hand guiding, we avoid the operator to move heavy loads. So we are also ensuring this regulation. And then we have also associated the generic robotic installation certifications on electrics, electronics, and this kind of things. And now we can move into one of the modes that I presented before, that is the speed and separation monitoring, or the SSM. Here, this solution is a safety system that works in open space. We have here a real-time control of the speed of the robot. So what we are doing is to monitor the distance between the operator and the robot, and depending on this distance and also the speed of the robot, we can control and modify the speed of the system. So with that, we define 3 modes. One is the stop mode, the second one is the reduce mode, and the normal functioning. And how we can do that? We can apply different type of technologies. We can use laser scanners, as you can see here from PIL. We can also apply ultra-wide bands or vision system. The selection of the system will depend on if we have some occlusions or another type of component. Depends on the lighting or what we can install and we have to monitor. And now this is the solution that we have here at AIMEN. Then we will see a video of this system working. And we are monitoring the people in the space with some camera visions and with artificial intelligence, and also a traditional vision like the OpenCV and the YOLO. We are obtaining the pose of the person. Here in this picture, you can see the skeleton of the person. And with that, we elaborate the digital twin of the person. And we do the same with the robot. We are extracting the positions and then elaborating the digital twin. So with that, we can, by software, we compute the distance between the 2 elements of the scenario. And depending on this distance, we send the command to the robot. And this is now not regulated, but we have to check how to do that, because now in 2027, a new machinery regulation will appear that covers all the part of the AI modules. Right now, the AI modules is not being regulated, so they are working on that. Okay, and now we can see the first video here on the. We can see the video of the SSM. We have here the robot performing an automatic task. Here you can see that we are obtaining the digital model of the cell with the camera systems and also with the driver with the robot. So with that, you can see now how the operator will approach to the robot, and the robot will stop. And when the operator leaves the area, the robot will go to normal mode again. So here you have seen how the robot was in normal speed, it reduced it, and now it is stopped. So we are having this system, and the benefits of using this system is that you don't have to put the system into an emergency stop or similar. So you ensure that all the system is working all the time and you're not stopping the production. Now you see how the operator leaves, and the robot will start moving again. Now it reduced, and now a normal speed. So this is the way we work with the SSM. And now we can move into the hand guiding. That it was another mode of the ISO that I commented before. And this solution is applied to move the robot by directly applying force on the end effector. We have a joystick integrated on it, so the operator can grasp it and apply the efforts into the direction of movement that he wants. And this is an intuitive way to work. So what we need to implement this solution? We need an industrial robot. Here we have developed it for an ABB and a KUKA robot. That is, I put here the models, but you can apply to all these kind of models of robots. Then we need a force and torque sensor. We are using the Shunk one, but any force torque sensor can be used. And the last element that we have is a joystick. We are using a one from ABB that has all the certification and is regulated. And we have some buttons to work with it. We have the Deadman switch that is the same as the ditch pendant one. And then we have general purpose switches that we can use it for storing points or interacting with the grippers, for example. And then in the software side, we have a hand-guiding module that computes the command to send to the robot based on the force and the robot position. So here we require high-speed communication with the robot around 250 Hertz. And this is critical because we are doing real-time control, so we need to send information so quick to the robot, because if not, we will not have the expected behavior of the robot. So just for curiosity, in ABB we have the external quiet motion, and in KUKA we have the robot sensor interface functionality. So with that we have implemented this system. And here you can see the architecture of the system. We have here the drivers of the components, and then the force sensor, the robot, and the joystick, and everything is based on TCP/IP communications. So now, once we have all the software and all the hardware, we need to do a previous steps like the calibration and configurations to be able to deploy this technology. So the first one is the Denavit-Hattenberg parameters. I don't know if you are familiar with this type of nomenclature of the robots, but this is a simplified way to represent the robot kinematics. So we have some restrictions when defining the reference systems. For example, you have to put the Z axis in the direction of movement of the joint and these kind of things. And with that, you compute the transfer between one joint to another one. So the result is that with 4 parameters, we represent this transformation. So it is quite optimal in computing, and it is quite easy to use. Then we have to define also in which position we have placed the sensor. Now we are defining it with respect to the TCP, and we have also to define the application point. This step is also crucial because if you program badly the application point, the robot will not move correctly, because we cannot translate correctly the information of the applied effort. The next step will be the sensor calibration. This step is also necessary to know in all the time which is the constant effort that is applied to the sensor and to the system. So with that, we can ignore this constant effort, and then we only read the effort applied by the robot. So for doing this calibration, we have to align each axis of the robot in both directions, in the positive and negative direction, with the gravity vector. So with that, we measure this effort. And the last step is to adjust the controller response. Here, the aim is to find the parameters that make the system move softly. We can adjust 3 parameters. One is the weight of the force and torque values, that is like a proportional value. We can adjust also the system inertia, that this will affect to the start and finish of the movement, which means that it's not hard to start moving the robot, but when you release the force, the robot will stop and will not have this inertia to continue with the movement. And the last point is the system friction, that is the resistance that we apply during the movement. So with these 3 parameters, we have to find the balance between all of them to find the desired movement for the robot in the way that is not difficult to start moving it, but you can have enough control of the system. And now, before going to our solution and see our solution, I want you to show the current solutions that are already in the market that are all based on collaborative robots. Here you can see the one for the FANUC robot and also for the UR robot. You can see that in the FANUC, the operator needs the 2 hands to move the robot. It is like a plugin that you put on the robot wrist. And in the UR, it is already implementing on it, and you can limit the axis of movement. You can block some rotations or some translations. And these are like the commercial solutions that we have. The problem when applying this is that we are using collaborative robots. We are not going to work in high speeds, and we can't move high payloads, because I think now the collaborative robots are around maximum 30-40 kilograms of payload. So in our case, the naval industry is not applicable to our solutions, because we are working with really heavy components. So here you can see the commercial solutions for hand guiding. And now we can move into our solution. We have developed for ABB and the KUKA and COMAU robots. The main difference here is the way that we command it. In both systems, we read the force supply and we transform into the robot commands. So in the ABB, we are directly sending the velocity that we extract from the controller. And in the KUKA and COMAU, we need an additional step, that is the transforming it to the position. And here we have seen that we need to apply some filtering techniques to have the smooth response. But in both ways, we are using the real-time control and all the capabilities that the robot has and the communication protocols. Okay, and now the applications that we are using here, then we see that it has more applications, but this is the 2 ones that we focus on. And we have the first one, the loads handling. We can move known loads and unknown loads. In the first case, we directly put the sensor on the robot wrist. And here we can only move known loads, because if you apply a known element, the calibration will be affected. So we only can work with this type of components. And just to remark that this application can also be useful to detect if you have grasped an object or not, because you know that, for example, you pick some component and then you see that the force that you're seeing is decreasing. So you know that there is some slippering and you're losing the object. So this is another thing that we can apply it for. And the second application is for unknown loads, that we integrate directly the joystick with the sensor. So we only read the effort applied by the operator. So it is more flexible solution. And the second application is the trajectory programming. We have here integrated the general purpose buttons and also the deadman switch. The deadman switch is for safety and to avoid the operator to be all the time grasping the teach pendant. Then the general purpose buttons are one for modifying the accuracy. With that, we modify the robot speed, so we have more control movement of the robot, or the robot will go faster, so we can have precise, more accurate and more precise movements, and also like a general movement. And the other button is used to store the trajectory points. Here we are also applying a graphical user interface to be more accessible for the operators, because this solution of programming trajectories, the aim is that the operator with no knowledge in robotics can use a robot and program a robot. So with that, for this reason, we provide a graphical user interface. In general, you can see here that you can modify the length of the trajectory, and also enable or disable the hand guiding module. Then you have some monitoring aspects, like you can monitor if the controller is active or inactive, and also the precision mode that you are working with. And it has some clear points button to, if you make some mistake, you can go back and restart programming the points. And then we have another button to execute the performance trajectory. So this is a video of the application of the trajectory programming. You can see here how the operator is moving the robot with the joystick and also the deadman button, and we are applying, we are pressing the store trajectory button, and we are storing, in that case, 3 points to perform an arc trajectory. So once we have all the trajectory stored, by using the graphical user interface, the robot is able to perform the whole trajectory that the operator wanted. So now we are doing some simulation of welding, but different applications can be used, because finally you have a gripper. If you change the gripper, you can uncover a lot of aspects. So with that, this is the first video, and the second one is more or less in the same way. Here we have the operator that is programming. Here is programming different points of the trajectory. You also have here a close view of the system, and it is programming a welding application also. So the objective here is that an operator that doesn't know how to manipulate a robot can really use it and program the points. So no knowledge is needed for doing that, only just to know how to use the hand guiding technology. Okay, so now here the operator has performed all the trajectory and stored all the points. Here, more points are defined in that case. And now the robot is performing a welding operation. So with that, this is a different type of application, but based on the same modules and the same ideas, programming trajectories or different things. And for example, here, if we have a gripper, we can grasp the element with the hand guiding, so we can move the different loads. And I think this is the last slide. We are going to focus into the application sectors. Now the solutions are for the naval and medical mechanics sector. We apply pick and place solutions, and also for welding, but we have seen that we can also apply it to the energy sector, or also aeronautics, mining, and automotive. More or less, the application is the same. In aeronautics, instead of welding, we can do some gluing, or we can use it for inspection in the way that the operator can move the robot to the interest area and then take some capture or similar to detect the components. Also for disassembly, it can be the application of moving loads. And just another thing that we have seen is in the automotive sector, we can use the hand guiding for safety purposes. For example, if a robot is stuck in some difficult position, then the operator can go and with the hand guiding move and put it into the safe position to continue with the automatic program. So we have seen these kind of applications. I think this is everything from my side. Thank you for your attention.
Thank you very much, Afra, for your presentation.